Here are our notes for inverse functions. I'm going to go through this first part pretty quickly. It's just a graphical introduction to what inverse functions are. If you need more time on this, you can pause and copy it or see the PDF in your Google Classroom. So it says, let's look at quadratic and square root functions, x squared, square root of x. They are inverses of each other, meaning that their x and y values are switched. And their graphs are reflections across the y equal x. So this has been reflected over here across this line. And it says fill in the table for each graph. So here are my domain and range for x squared. And then if you literally just flip these two columns, you get the x and y table for the square root of x. Now we've talked before about how this solid red line right here, this is actually the graph for the square root of x. But I have gone ahead and filled in these dots here, the 4, -2, 1, -1. You see how that's a dashed line? This is actually undefined for the graph because you can never actually have negative y values for a square root of x, not in the real number system. So these are actually undefined, and but I wanted to preserve the shape to let you see how the original parabola was reflected down here. But really, just the solid one is the square root of x. But the larger picture is just that they are inverses of each other by switching their x's and y's. And here is their graph. What we're going to do in the next section is use these two functions to find f of g of x and then g of f of x. This is a function composition that we talked about in the last unit. And remember, that's where you take one function and plug it into another function. You substitute one function into another function for the x value. So I'm first going to do f of g of x. So this means I'm going to take the g function and plug it into the f function. So my g function is the square root of x plus 5. I'm going to take this whole thing over to the f function and replace x with it. So I've got the square root of x plus 5. Now because that's replaced x and x was squared, this needs to be squared. And then I have the minus 5. And so now the instructions say to simplify that. So I notice that the square cancels out the square root, leaving me x plus 5. And then I have this minus 5. And now the 5's cancel each other out, leaving me just x. Right? So now I'm going to see what happens when I do composition of functions by plugging f into g. So I'm going to do the second one. This notation means take the f function and plug it into the g function. So my f function is equal to x squared minus 5. I'm going to go over to g and replace x with this entire expression. So x is getting substituted with x squared minus 5. And then I still have that plus 5 in the square root. So now working inside here, I see that the negative 5 and the positive 5 cancel, leaving me square root of x squared. And the square root cancels out the squared, leaving me just x. Now what we've just done is shown that the composition of functions in either direction, whether g goes into f or f is subbed into g, both of them simplify to x. And this is a mathematical proof or an algebraic proof that these functions are inverses of each other. So if f of g of x simplifies to x and g of f of x simplifies to x, then the functions are inverses. So if we were to graph them, they would reflect over this y equals x. If you made a table of them, their x's and y's would be switched. So I want you to pause the video and try that with this problem right here. Instead of f and g, you have h and k, so you want to plug k into h, simplify, and then also plug h into k. So pause the video and try that. Okay, so here I have my setup for each composition. In number 1, I have taken the k function and substituted into h. So I took all of this and substituted in here for x. So there's my k function there, and then the plus 3 squared minus 7. So working inside the set of parentheses, I can tell that the 3's cancel, leaving me the square root of x plus 7 squared minus 7. And now this squared cancels out this square root, leaving me x plus 7. Then the minus 7 comes down. And now the 7's cancel, leaving me x. Now I'm not done, so I have shown that it's x for substituting k into h, but now I still have to show that it's also x substituting h into k. So I took h, which was all of this, over here and replaced just the x with it. So that's what I have right here, the x plus 3 squared minus 7. This plus 7 comes from the k function, and then I have the minus 3 from there as well. So working inside this radical, I see that the 7's cancel. Leaving me the x plus 3 squared inside the square root, the minus 3 from outside. The square root cancels the square, leaving me x plus 3, and then bring down the minus 3. And now those 3's cancel, leaving me just x. So I did verify that these functions, yes, are inverses of each other. Now, we talked graphically about what inverse functions are. We used algebra to verify that functions were inverses, 2 functions. And now what we're going to do is be given just one function, and we are going to derive its inverse. So these are the basic steps here. So you'll see I'm given a function, just one this time, and I want to find the inverse. So my steps are to switch x and y, which makes sense based on our definition from the front, solve for y, and then use inverse function notation for your new equation. So I'm going to start out by switching the x and y. And then I start to solve for y. I'm going to add 3 to both sides. X plus 3 equals y over 2. Now I need to multiply both sides by 2. So on the right, the 2's cancel, leaving me y. And on the left, I'll need parentheses around the x plus 3 because it's 2 times this entire group. And you can leave it like this or distribute and make it 2x plus 6. And then use your function inverse notation. We can write f inverse of x. I would take just y inverse as well, whichever you're used to writing. And just remember that this is not a negative power or exponent, mathematically speaking. It's just symbolic notation saying that you took the inverse of this function. So you pause, and I want you to try example 2. All right, so the first step here, again, is to switch the x and the y. So x equals 4 cube roots of y plus 2, and then minus 5 on the outside of the radical. So now I need to get y isolated, but there's a lot happening. There's a plus 2 inside, there's a cube root of 3 times 4, and a minus 5. So we're going to start at the operation that's farthest away from the y, which is this minus 5. So I add 5 to both sides. So the next thing I want to do is handle this multiply by 4. I'm going to divide by 4. And on the left, the entire thing gets divided by 4. So now I'm here. So now that the radical is isolated, I'm going to undo that by taking the cube of both sides. So the cube cancels out the cube root. Now I have one more step to get the y by itself. I need to subtract 2 to both sides. And you can do y to -1 or f -1, whichever you like. Okay, and then pause and try this last one by yourself as well. All right, step 1 is to switch your x and y. And then step 2 is to solve for y. So right now I have y is squared times a half and then a plus 1. So I'm going to start at this plus 1, which is like the far, air quote, can you see my air quotes? Farthest away. So minus 1, minus 1. So x minus 1 equals 1/2 y squared. So the next thing, I'm going to undo the 1/2 by multiplying both sides by 2. So, and just like earlier, 2 times a group, I'm going to put that group in parentheses. You could also distribute, if you like, 2x minus 2. And now that the y square is isolated, I'm going to get rid of the square by square rooting both sides. And that's what equals y, or y negative 1. You can write the 2 here for the root or don't. Square root can be understood as a 2 when you don't write it.